Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Sophia Chen. Of all the colors of light-emitting diodes, or LEDs, the blue ones are especially tricky to make. That's because among the red, green, and blue photons that combine to make the white light on your computer screen, blue photons have the highest energy. This means the material that emits the blue photons has to have a wide bandgap, and wide bandgap materials are inherently harder to grow, process, and integrate into efficient devices. Ultimately, to make bright and stable LEDs, engineers have needed to use expensive and energy-consuming processes to design and put together the materials that emit the light. Jing Li, a chemist at Rutgers University, has developed a new material for making blue LEDs, along with a method for making them that uses a solution-based manufacturing process.
We fabricated the solution process, the deep blue LED, using the type of material that has never been used in the past for this type of application.
A solution-based manufacturing process should be a lot more energy efficient than existing processes for making blue LEDs that involve vapor deposition or require vacuum. It has other potential advantages as well.
The process is inexpensive, and also, they are very robust and do not contain any toxic elements such as in perovskite-based LEDs.
The basis of any LED is a material that emits light when electricity is applied. The emitting material they designed is a hybrid material of copper-iodide and organic ligands known as HDAPCO. The material emits deep blue light at 460 nanometers. Qin Zhu, a chemist at the Max Planck Institute of Microstructure Physics who worked with Li, explains.
It has a unique structures and it's having a good photophysical properties as well as charge carrier transport properties.
They made a prototype of 8 LEDs on a substrate of 4 square centimeters in area. Each LED consists of several layers, of which the emitter is one layer. First, you start with a 1.2 millimeter substrate made of indium tin oxide, which serves as an electrode. Above the indium tin oxide, they put a single molecular layer of the self-assembling polymer, polymethyl methacrylate. Then, an 85 nanometer layer of the emissive hybrid copper-iodide material goes on top of the polymer, which formed hydrogen bonds with the emissive material. These hydrogen bonds serve two purposes. They make the hybrid material less reactive, which improves the LED's stability. The hydrogen bonds also help introduce electrons and holes and balanced numbers into the emissive material, allowing it to emit light more efficiently.
This dual hydrogen bonding approach is a novel one, and nobody has done it before.
We could increase both the performance of these LEDs, at the same time increase the operational stability of it.
To manufacture the LED, they spin the substrate in vacuum at about 2,000 times per minute and drop the materials onto the substrate.
The high spinning will just remove all the excess amount of the solutions and also the small solvent molecules, only leaving the thing you want to deposit on the surface. And then you can do post-treatment, including anti-solvents, vapor-assist annulings at certain conditions to get the things you dissolved back into its solid state.
They have ways of improving the process further.
In the future, we could do spray coatings, which is more energy efficient.
Their material achieved a maximum external quantum efficiency of 12.57%. In essence, this is the percentage of the electrical energy that gets converted into light. The value might not seem high, but Li says it beats out similar blue LEDs made of hybrid materials using similar solution-based processing. Those achieve only around 10% efficiency.
That's why our number still stands high.
Their method also potentially allows them to make large arrays of LEDs at once.
We're trying to directly make them into a large area LED device so that it could be directly used as a screen.
However, they still have to improve the LED's stability before it can be commercialized. They achieved an operational stability half-life of 204 hours. Operational stability is an industry standard that measures how long a light can stay consistently bright. Commercial blue LEDs might have a half-life of more than 10,000 hours, Zhu says. This work was published in a recent issue of Nature. My name is Sophia Chen from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on X @MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.